Picture a single point. Not a point you could mark with a pen, not a speck of dust, not even a single atom. Smaller than that. Smaller than anything you have ever tried to imagine. Smaller than the width of a proton divided by 100 trillion trillion. A point so compressed that the very notion of here and there no longer applies. Inside that point, according to the equations we have trusted for a century, space curves so violently that it folds over on itself and stops. Time does the same. The mathematics simply halts, mid-sentence, like a book with its last pages torn out. For most of the 20th century, physicists gave that point a name. They called it a singularity, and they moved on. But here is the part they did not tell you. The singularity was never a prediction. It was a confession. It was the place where the theory we use to describe gravity, Einstein's general relativity, breaks down so completely that it cannot tell us what happens next. A singularity is not a thing. It is an admission. It is physics raising its hands and saying, I don't know. And yet, for decades we drew diagrams of black holes with singularities at the centre as though they were real objects. We calculated their masses, their spins, their electric charges, and we quietly accepted that at the heart of each one lay a point where all our rules expire. We did this because we had no better story. The mathematics demanded it, and the mathematics had been tested 12 decimal places in every other regime, so we assumed it must be right even in the places we could never see. Now consider this. A small but growing number of physicists believe the singularity does not exist. They believe that when matter falls into a black hole and reaches the point where space-time is supposed to end, something else happens. Something stranger and gentler than infinite collapse. The matter does not vanish. It does not halt. It bounces. It bounces and emerges somewhere else. The equations that suggest this are not speculation. They come from a program called loop quantum gravity, built over 30 years by hundreds of researchers, and they're among the most mathematically rigorous attempts we have to unite Einstein's curved space-time with the strange probabilistic rules of quantum mechanics. One of the central figures in this effort is Carlo Rovelli, an Italian theoretical physicist who has spent much of his life studying what happens when you push Einstein's equations past their limits and ask them to make peace with quantum theory. And what Rovelli's calculations suggest, what the calculations of many people in this field suggest, is that a black hole, at the end of its life, does not simply fade away. It transforms. It tunnels through a quantum barrier and re-emerges as something we have always thought was merely a time-reversed fantasy. A white hole. If that sounds abstract, let me put it more plainly. Imagine dropping a ball. It falls, hits the ground, stops, and then, without any additional push, bounces back up and falls upward into your hand. That is what a white hole does to everything that ever fell in. It is a black hole played in reverse, spitting out the light and the matter and the time that once fell beyond the horizon, returning it to the universe from which it came. Now extend that picture. What if the universe itself, the whole of space, every galaxy, every photon, every atom of your body, is simply the inside of such a bounce? What if the Big Bang was not a beginning at all, but a passage? A doorway that looks like a birth from this side, but from the other side looks like a collapse? There is a second physicist whose name belongs in this story. His name is Nicodem Popławski, and he works at the University of New Haven in Connecticut. For more than a decade, Popławski has been building a picture of cosmology in which our entire observable universe sits inside a black hole that formed in a larger parent universe. In his model, the Big Bang was the moment when collapsing matter in that parent universe reached the density where Einstein's equations would normally break down, and instead of forming a singularity, the matter bounced outward into a new region of space-time, a region that became us. These two ideas, Rovelli's quantum bounce and Popławski's universe inside a black hole, are not identical. They come from different mathematical frameworks, different starting assumptions, different communities of researchers, but they share a spine. They share the conviction that the singularity is a failure of imagination, not a feature of nature. They share the suspicion that gravity and quantum mechanics, properly combined, will never allow space-time to simply end. And they share a haunting implication, that the violent collapse at the heart of every black hole may be a birth canal, not a grave. If you stay with me over the next 2 hours, we are going to walk through this slowly. We will ask what a white hole actually is, not as a phrase, but as a shape in the mathematics of space-time. We will ask why loop quantum gravity predicts a bounce instead of a stop. We will spend time with a deeply strange number, the tunneling time, the duration it takes for a black hole to transform into a white hole. From the outside, that time looks almost identical to the lifetime of Hawking evaporation, perhaps 10 to the power of 67 years for a black hole the mass of the Sun. From the inside, it may be instantaneous. We will examine the observable signatures, primordial black hole bursts, subtle asymmetries in the cosmic microwave background that might just possibly betray this process, and we will end in a quiet place. A place where the Big Bang is not a mystery of origin but a consequence of collapse, where our cosmos is one link in a chain that may stretch backward forever through parent universes and grandparent universes, each one seeding the next through its heaviest, most crushed remnants. If these ideas are right, we're not living at the beginning of anything. We are living in the middle of a story that began somewhere else. Consider tapping that like button and subscribing if these slow journeys through the deep help you settle in. Now, let us begin. To understand why physicists talk about bounces inside black holes, you need to understand what a black hole is, not as an image, not as a metaphor, but as a shape. Space-time is not flat. Mass and energy warp it, bend it, curve it the way a bowling ball dimples a rubber sheet. Einstein's great insight was that this curvature is gravity. Objects moving through curved space-time follow the straightest paths they can, and those paths lead them toward mass. A black hole is simply a region where the curvature has become so extreme that no path leads outward. Every trajectory, no matter how fast, no matter what angle, bends back toward the center. There is a surface, the event horizon, that marks the point of no return. Cross it, and you are no longer choosing whether to fall. You are already falling. The inward direction is no longer a direction in space. It has become a direction in time. The center is not a place you can avoid by steering. It is your future. This is the part most people know. But here is the part fewer people think about. General relativity does not actually say what happens at the center. It says that as you approach the center, the curvature grows without bound. Density climbs toward infinity. Tidal forces stretch and compress you with infinite violence, and then the equations produce a divide by zero, and they stop. A singularity, in mathematical terms, is not a place. It is the absence of a place. It is the boundary where the equations can no longer describe space-time at all. And for most of the 20th century, physicists assumed this was simply the way black holes worked. The singularity was hidden behind the event horizon, so it could not affect the outside universe. The equations described everything we could observe. The breakdown at the center was philosophically uncomfortable but practically irrelevant. Then came a shift. It began, in some sense, with Stephen Hawking. In the 1970s, Hawking showed that black holes are not perfectly black. Quantum effects near the event horizon cause them to radiate a faint glow, a thermal spectrum with a temperature inversely proportional to their mass. A black hole the mass of the Sun would have a temperature of about 60 billionths of a degree, above absolute zero, far colder than the faint warmth of the cosmic microwave background. Such a black hole would absorb more radiation than it emits and grow slowly over time, but Hawking also showed that if you wait long enough, if you wait until the universe expands and cools and empties, until the background radiation fades to nothing, a black hole will find itself in a universe colder than it is, and then it will lose mass. Particle by particle, photon by photon, it will radiate away its substance. The process is almost incomprehensibly slow. A black hole the mass of the Sun would take 10 to the power of 67 years to evaporate, a 1 followed by 67 zeros. That is longer than the current age of the universe by a factor of about 10 to the power of 57. But it happens, and as it happens, the black hole shrinks. Its event horizon contracts. The singularity, if it exists, draws closer to the edge, and at the very end, when the black hole has dwindled to a mass of a few micrograms, the curvature at the horizon becomes comparable to the Planck scale, the domain where general relativity and quantum mechanics collide. Hawking's calculation is elegant. It is also disturbing. It produces a paradox called the information problem, which we will touch on later. But for our purposes tonight, the key point is simpler. Hawking evaporation means black holes have a life cycle. They are born from the collapse of massive stars. They feed on matter and light. They grow, and eventually, over timescales too long for the human mind to grasp, they die. The question is, what do they die into? For Hawking, the answer was radiation. The black hole simply evaporates until nothing remains but a diffuse fog of particles scattered across the void. The singularity vanishes with it somehow, and the space-time where the black hole used to be is restored to flatness. But Hawking's calculation was done in a framework called semi-classical gravity. It treats space-time as a smooth classical background and sprinkles quantum fields on top. It does not treat space-time itself as quantum. It does not ask what happens to the singularity when quantum effects become strong enough to matter. And when you do ask that question, when you build a framework in which space-time itself is quantized, in which geometry has a granular structure at the Planck scale, you get a different answer. You get a bounce. Loop quantum gravity was not built to explain black holes. It was built to answer a more fundamental question. Can you quantize gravity the same way you quantize everything else? Quantum mechanics tells us that energy comes in discrete packets. Light is made of photons. Matter is made of particles. Fields are made of quanta. Every force in nature, when examined at small enough scales, reveals a granular structure. Electromagnetism, the strong nuclear force, the weak nuclear force, all of them can be described as quantum field theories, where smooth classical fields dissolve into clouds of interacting particles. Gravity resists this treatment. It is not a force carried by particles moving through a background space-time. It is space-time. The curvature of geometry is the gravitational field, and when you try to quantize geometry the way you quantize other fields, you run into infinities that cannot be removed by any known mathematical trick. For decades, physicists assumed this meant gravity was fundamentally different. String theory, the most famous attempt at quantum gravity, solves the problem by adding extra dimensions and replacing point particles with tiny vibrating loops. Loop quantum gravity takes a different path. It accepts the 4 dimensions we observe and asks, what if space-time itself is not continuous? What if, at the Planck scale, around 10 to the minus 35 meters, roughly 100 billion times smaller than a proton, geometry is made of discrete building blocks? The name comes from the mathematics. In loop quantum gravity, the quantum states of geometry are described by networks of loops called spin networks. These loops carry discrete chunks of area and volume. There is a smallest possible area, about 10 to the minus 70 square meters. There is a smallest possible volume, about 10 to the minus 105 cubic meters. Below these scales, the concept of smooth, continuous space simply does not apply, and this discreteness has a consequence. When you track what happens to space-time inside a collapsing star, when you follow the matter inward toward the place where general relativity predicts a singularity, the loop quantum gravity equations do something different. The curvature rises, the density climbs, but there is a ceiling. The quantum structure of space-time resists compression beyond a certain point. The collapse does not halt exactly, but it rebounds. The matter passes through a quantum transition and begins to expand outward again. This is the bounce. Let that settle for a moment. The mathematics says, in a framework that is still being developed, still being tested, still incomplete, that when matter crosses the threshold where general relativity breaks down, it does not stop. It transforms. It tunnels through a quantum barrier from a contracting geometry to an expanding geometry. It emerges on the other side, moving outward instead of inward, and the geometry of that outward moving region is not a black hole. It is a white hole. A white hole is not a new idea. It is as old as general relativity itself. When you write down the equations for the simplest possible black hole, the Schwarzschild solution, discovered in 1915, you find that the mathematics contains a kind of mirror image. The same equations that describe a region from which nothing can escape also describe a region into which nothing can enter. One is a black hole, the other is a white hole. Picture it this way. A black hole has a horizon that you can cross going in but not going out. A white hole has a horizon that you can cross going out but not going in. A black hole is a one-way door leading inward. A white hole is a one-way door leading outward. Inside a black hole, all paths lead toward the singularity. Inside a white hole, all paths lead away from it. Matter and light that find themselves inside a white hole have no choice but to exit. They are expelled, flung outward, returned to the universe. For most of the 20th century, white holes were treated as mathematical curiosities. They appear in the equations, yes, but the equations describe an eternal, idealized space-time, not the messy astrophysical universe we actually observe. A real black hole forms from the collapse of a massive star. The white hole region of the Schwarzschild solution, which exists only in the past of the black hole, was thought to have no physical relevance. It was a ghost in the geometry, an artifact of extending the equations beyond their domain of applicability. But Rovelli and his collaborators saw something different. They noticed that if you allow quantum transitions between geometries, if you accept that spacetime at the Planck scale is not smooth but granular, and that granular systems can tunnel from one configuration to another, then the interior of a black hole does not have to remain a black hole forever. It can transition through a quantum process into a white hole. The picture is roughly this: collapse a star. It forms a black hole with an event horizon and an interior that, according to classical general relativity, ends in a singularity. But at the Planck scale core, where the curvature would become infinite, the quantum structure of spacetime intervenes. The collapsing geometry tunnels through a barrier. On the other side, it is no longer collapsing, it is expanding. The geometry is now that of a white hole, not the idealized eternal white hole of the textbooks, but a white hole born from the death of a black hole. The matter that fell in now falls out. The light that was swallowed is released. The event horizon, which once marked the point of no return, becomes a boundary from which everything returns. And here is the strange part, the part that makes this more than a mathematical exercise. From the outside, this process looks almost exactly like Hawking evaporation. Let me explain what I mean. Quantum tunneling is not instantaneous, but it happens on timescales that depend on the size of the barrier and the energy of the system. For a stellar mass black hole, one with a mass between a few and a few tens of times the mass of the Sun, the tunneling time is extraordinarily long. Rovelli's group has estimated it at something like 10 to the power of 60 years, perhaps longer. This is the timescale for the quantum transition to occur, for the black hole to transform into a white hole. Compare that to Hawking's evaporation time. A stellar mass black hole takes roughly 10 to the power of 67 years to evaporate. The numbers are not identical, but they are in the same cosmic ballpark. Both are durations so long that the current age of the universe, 14 billion years, is a rounding error by comparison. This similarity is not a coincidence. Rovelli and his collaborator Francesco Vidotto have argued that what we call Hawking evaporation and what they call the black to white hole transition are two descriptions of the same process, seen from different vantage points. Think about what Hawking radiation looks like from the outside. The black hole shrinks, its mass decreases, its horizon contracts. At the very end, in the final instance of evaporation, the black hole reaches Planck scale dimensions and releases a burst of high-energy radiation. Then, it is gone. Now think about what the bounce looks like from the outside. The black hole sits there, apparently static for a vast stretch of time. Then, at some point, the quantum transition completes. The horizon transforms from a black hole horizon into a white hole horizon. The matter that was inside is expelled. A burst of energy emerges. The white hole, having released its contents, fades away. From the outside, these two stories look similar. Both involve a long wait followed by a sudden burst. Both end with the disappearance of the black hole. The difference is in what happens to the information, the quantum states of the matter that fell in. In Hawking's original picture, that information is lost. The radiation is thermal, meaning it carries no detailed imprint of what fell in. This is the information paradox. Quantum mechanics says information cannot be destroyed, but Hawking's calculation says it is. In the bounce picture, the information is not lost. It falls in, bounces, and comes back out. The white hole expels everything the black hole ever swallowed, encoded in the quantum states of the emerging matter. Information is preserved, and the paradox dissolves. Whether this resolution is correct, whether Rovelli's bounce is the right answer to the information problem, is still an open question. But the proposal is mathematically concrete. It makes predictions, at least in principle, and it offers a picture of black hole death that is not evaporation but transformation. But here is where the strangeness deepens. We have been talking about what the bounce looks like from the outside. What does it look like from the inside? Imagine you are falling into a black hole. You cross the event horizon. The sky behind you closes like a door. You feel no sudden jolt. The event horizon is not a physical barrier, just a boundary in the geometry of space-time. You continue falling, accelerating as the curvature around you grows. In classical general relativity, your fate is sealed. The singularity lies ahead, and you will reach it in a finite time, perhaps microseconds, perhaps less, depending on the black hole's mass. Time itself funnels you toward the end. But in loop quantum gravity, the singularity is replaced by the bounce. You fall inward, the curvature rises, and then, at the Planck scale, something shifts. The geometry transitions from collapse to expansion. You are no longer falling inward, you're moving outward, you're inside a white hole now, and the horizon you crossed going in is now a horizon you must cross going out. And here is the key. From your perspective, this happens almost instantly. The bounce is a quantum transition, and quantum transitions, from the perspective of the system undergoing them, take negligible time. You fall in, you bounce, you come out. The whole journey feels brief. Perhaps a fraction of a second, perhaps less, depending on the details. But from the outside, the black hole has been sitting there for 10 to the power of 60 years. This is not a paradox. It is relativity pushed to an extreme. Time flows differently near a black hole. Near the event horizon, time slows. At the horizon, from the perspective of a distant observer, time stops. An observer watching you fall in sees you frozen at the horizon forever, or at least for so long that all the stars burn out and the universe goes cold before you appear to cross. The same effect applies to the bounce. From the inside, the transition is fast. From the outside, the transition is slow. The interior clock and the exterior clock are radically out of sync. The bounce happens in an instant on one side of the horizon and takes aeons on the other. And so the black hole appears to sit there, unchanging, for an unimaginable span of time. Then, suddenly, from the outside perspective, it is done. The white hole emerges. The expelled matter streams outward. The long wait is over. Let me put this another way. If you fell into a black hole that formed from a collapsing star and you experienced the bounce, you would emerge, in your subjective time, almost immediately. But the universe you emerged into would be unrecognizably old. The stars of your era would be long gone. The constellations would have dispersed. The cosmos would be dark and diffuse, filled with the cooling remnants of everything that once burned. You would have travelled forward in time without meaning to. The bounce is a time machine, though not a useful one. Rest with that for a moment. Now, I want to widen the lens. Rovelli's picture describes what happens to a single black hole, a stellar remnant perhaps, or a supermassive black hole at the centre of a galaxy. But there is another physicist whose work asks a different question. Not what happens when a black hole dies, but what happened when our universe was born. Nikodem Popławski began with a puzzle that has troubled cosmologists for decades. The Big Bang, as traditionally described, is also a singularity. Wind the clock backward, compress the universe smaller and smaller, and you reach a point where all the matter and energy we observe today was packed into a region of infinite density. The equations of general relativity applied to the early universe produce the same breakdown they produce inside a black hole. The curvature diverges. Time, traced backward, runs out. The theory has no answer to the question, what came before? Popławski's insight was to notice that Einstein's general relativity is not the only possibility. There is an extension of the theory, not a rival, but a completion, that includes a property of matter called torsion. Torsion is related to spin. In standard general relativity, mass curves space-time but leaves it smooth. In the extended theory, called Einstein-Cartan theory, spinning matter twists space-time as well as curving it. This torsion is normally negligible, but it becomes important at extreme densities, exactly the densities reached at the core of a black hole, or in the earliest moments of the Big Bang. And when Popławski solved the equations of Einstein-Cartan theory for collapsing matter, he found something remarkable. The collapse does not reach a singularity. At a certain critical density, around the Planck scale, the torsion terms become repulsive. They push back against the collapse. The matter bounces outward, just as in loop quantum gravity, and expands into a new region of space-time. But here is the twist. The new region of space-time is not the same universe. It is a separate universe, connected to the parent universe only through the throat of the black hole. The black hole's interior becomes the entire cosmos of the baby universe. The Big Bang in this picture was the bounce at the core of a black hole that formed in a larger, older space-time. Let me say that again. In Popławski's model, our universe is the inside of a black hole. The Big Bang was not the beginning of time. It was the moment when collapsing matter in a parent universe reached the quantum gravity regime and rebounded outward, inflating into everything we see today. From the perspective of an observer in the parent universe, the black hole looks like an ordinary black hole. It has a mass, perhaps a few solar masses, perhaps much larger. It has a horizon. It sits there, slowly evaporating or perhaps growing as it feeds on ambient matter. From the outside, there is no sign of the universe within. But from the inside, from our perspective, that same black hole is the entire cosmos. The expanding space we observe, the galaxies receding from each other, the cosmic microwave background, the large-scale structure, all of it is the interior of a collapse that, thanks to torsion, became a birth. And the parent universe is unreachable. We cannot send signals back through the horizon. We cannot even, in principle, confirm that it exists. We can only infer it from the mathematics, from the equations that say the singularity does not happen, the bounce does. Let that settle. There is a symmetry here that deserves attention. Rovelli's picture says that black holes in our universe bounce and become white holes. Popławski's picture says that our universe itself is the result of a bounce inside a black hole somewhere else. The two ideas are not in conflict. They are nested. Imagine a chain. A black hole forms in some ancient parent universe. The matter at its core reaches the Planck density and bounces, spawning a new universe, ours. Inside our universe, new black holes form, from collapsing stars and merging remnants, and perhaps primordial fluctuations in the early cosmos. Each of those black holes, in turn, contains a core that bounces. Each bounce might seed another universe, another link in the chain. The chain could extend backward forever. There may be no first universe, no ultimate origin, no moment of true creation. Just collapse and bounce, collapse and bounce. Each universe the child of a black hole in the one before. This is speculative. It rests on frameworks, loop quantum gravity, Einstein-Cartan torsion, that are still incomplete, still debated, still in need of observational tests. But it is not mere fantasy. The mathematics is rigorous. The proposals are falsifiable, at least in principle, and the picture they paint is coherent. Singularities do not exist. Gravity and quantum mechanics together enforce a bounce, and what looks like an ending from one perspective is a beginning from another. Now, before we continue, I want to pause and acknowledge what we are doing here. We are taking ideas from the frontier of theoretical physics, ideas that most physicists have not yet accepted, that may turn out to be wrong, that are still being refined and challenged and tested, and we are walking through them as though they were stories. They are stories in a sense. They are narratives about the structure of reality, built from equations and observations and careful reasoning. But they are stories where the ending is not yet written. Nobody knows whether loop quantum gravity is the correct theory of quantum space-time. Nobody knows whether Popławski's torsion model is the right way to complete general relativity. The observed universe has not yet told us which picture is true. What we can say is that these ideas take the singularity problem seriously. They refuse to accept that space-time simply ends at the center of a black hole. They demand that a complete theory of gravity explain what happens there, and when they work out the consequences, they find bounces, white holes, nested universes, chains of creation stretching back without beginning. Whether nature agrees remains to be seen. But this is how physics has always worked. Ideas are proposed, predictions are made, observations are gathered. The ideas that survive the test become part of our understanding. The ones that fail are discarded or revised. The process is slow, and it is humbling. But it is the only way we know to approach the truth. In the sections that follow, we will go deeper. We will look at the precise mechanism of the quantum bounce, how loop quantum gravity replaces the singularity with a Planck scale transition. We will explore the tunneling timescale in more detail and ask what happens to a black hole over durations we cannot truly imagine. We will examine the observational signatures, the burst from primordial black holes, the subtle asymmetries in the cosmic microwave background that might, just possibly, allow us to distinguish the bounce picture from its rivals. And we will return, again and again, to the quiet possibility that sits beneath all of this. that the Big Bang was not a beginning, that the universe we call home is one room in an infinite hotel, and that every black hole in the night sky might be, from the inside, a cosmos just like ours. The stars are not the end of the story, they may be the beginning of someone else's. Let us begin then with the bounce itself. To understand what loop quantum gravity proposes, you need to set aside the smooth, continuous fabric of space-time that Einstein gave us. That fabric is beautiful. It curves and stretches and warps around mass and energy, and for a century it has passed every test we have thrown at it. But it is classical. It treats space and time as continuous quantities, infinitely divisible, capable of being measured to any precision you like. And when you push it to the extreme, when you ask what happens at the very centre of a black hole, where all the mass is compressed into a point of zero volume, it breaks. The curvature becomes infinite. The density becomes infinite. The equations produce infinities, and infinities are not answers. They are confessions of ignorance. Loop quantum gravity takes a different starting point. It says that space itself is not continuous. It is woven from discrete threads, tiny loops of gravitational field, each one carrying a quantum of area or a quantum of volume. The metaphor of a fabric is not quite right, because a fabric can be magnified forever, and you will always see more threads. In loop quantum gravity, the magnification stops. There is a smallest possible area, a smallest possible volume, a fundamental grain to the geometry of the universe. That grain is set by the Planck scale, a length of about 10 to the minus 35 meters, a time of about 10 to the minus 43 seconds, an energy density beyond anything we can produce in any laboratory. At everyday scales, you would never notice. The graininess is so fine that space appears perfectly smooth, just as a digital photograph appears continuous until you zoom in far enough to see the pixels. But at the Planck scale, the discreteness matters, and it changes everything about what can happen at the centre of a black hole. Picture the collapse again. A massive star exhausts its fuel, the core falls inward. Gravity pulls the matter tighter and tighter, and in classical general relativity, the compression continues without limit until all the mass occupies a single point of infinite density. But in loop quantum gravity, the compression cannot continue without limit. As the density approaches the Planck density, roughly 10 to the 93 grams per cubic centimetre, a number so large it resists comprehension, the discreteness of space-time asserts itself. The usual attractive force of gravity is opposed by a repulsive pressure that arises from the quantum geometry itself. This is not a force you put into the theory by hand. It emerges from the structure of the quantum gravitational field. It is a consequence of the loops, the grains, the fundamental discreteness, and it is enormous. At Planck density, this quantum gravitational pressure becomes strong enough to halt the collapse. The matter, still falling inward at tremendous speed, encounters a floor it cannot penetrate. It bounces. The bounce is not gradual. It is not a gentle slowing followed by a reversal. It happens in an instant, a Planck time, a flash so brief that it barely qualifies as duration at all. One moment the matter is compressing toward maximum density. The next, it is expanding outward, rushing away from the point where the classical singularity would have been. The singularity never forms. The density reaches a finite maximum, the Planck density, and then decreases as the matter spreads out again. This is the quantum bridge, the smooth throat of space-time that we mentioned before. The tunnel connecting the black hole to its white hole future is not an arbitrary addition to the theory. It is what the mathematics produces when you quantize gravity. When you apply the rules of quantum mechanics to the gravitational field, the singularity is replaced by this Planck scale region of maximum curvature. And on the other side of that region, space-time continues. The collapse becomes an expansion. The black hole becomes a white hole. Let that settle for a moment. The bounce is the core of the proposal. Without it, there is still a singularity, still an edge to space-time, still a place where physics breaks down. With it, there is continuity. The matter that fell into the black hole does not vanish. It passes through the quantum bridge and emerges on the other side, transformed but not destroyed. And from the perspective of that matter, from the perspective of anything falling along with it, the transition is instantaneous. The bounce happens in a Planck time, too fast for any internal process to register, too fast for any clock to tick. But from the outside, the story is very different. Here is where the two timescales diverge in a way that can make your head spin if you let it. From outside the black hole, the bounce is not instantaneous. It is unimaginably slow. Remember that time behaves strangely near a black hole. As you fall toward the event horizon, your clock runs normally. To you, each second feels like a second, each minute like a minute. But to someone watching from a safe distance, your clock appears to slow down. As you approach the horizon, it slows more and more. At the horizon itself, it appears to stop. A distant observer would never see you cross the event horizon. They would see you frozen there, reddened and dimmed by the gravitational redshift, growing fainter and fainter but never quite disappearing. This is not an illusion. It is a genuine effect of general relativity. Different observers in different gravitational fields experience time at different rates. The flow of time is not absolute. It is local, personal, dependent on where you are and how you are moving. Now apply this to the bounce. From the perspective of the infalling matter, the bounce happens in a Planck time, but from the perspective of a distant observer, that Planck time is stretched by the extreme gravitational time dilation near the event horizon. It is stretched not by a factor of 10 or a million or a trillion, but by a factor that depends on the mass of the black hole and the details of the quantum gravity theory. And the stretching is staggering. For a stellar mass black hole, the kind formed when a massive star collapses, the bounce time as seen from outside is roughly comparable to the Hawking evaporation time. A stellar mass black hole, left alone without any matter falling in, would take about 10 to the 67 years to evaporate through Hawking radiation. That is a number that makes the current age of the universe, 14 billion years, or about 10 to the 10 years, look like a rounding error. The bounce, as seen from outside, takes about that long. For a supermassive black hole, the kind that sits at the centre of a galaxy, the timescale is even longer. Sagittarius A, the black hole at the heart of the Milky Way, has a mass of about 4 million suns. Its Hawking evaporation time, and therefore, roughly, its external bounce time, is something like 10 to the 83 years. Write that out, a 1 followed by 83 zeros of years. The universe as we know it will have long since gone cold and dark. Every star will have burned out. Every galaxy will have dispersed. The cosmic background radiation will have cooled to a temperature indistinguishable from absolute zero. And still the black hole will be sitting there, slowly, slowly, slowly completing its quantum bounce. Try once more to give that scale a shape. If the current age of the universe were 1 second, the bounce time for a supermassive black hole would be longer than the age of the universe counted out in seconds. It would be longer than the number of atoms in the observable universe. It would be longer than the number of possible games of chess. It is a timescale so vast that it threatens to become meaningless, a number too large for the human mind to hold. And yet, from the inside, it is instantaneous. The matter falls in, reaches Planck density, bounces, and emerges as a white hole and experiences no time at all. The two perspectives are equally valid. Neither is more real than the other. They are simply different views of the same event, filtered through the strange geometry of space-time near a horizon. This is one of the reasons the black-to-white hole picture was not taken seriously for so long. The external timescale seemed to make it irrelevant. If the bounce takes 10 to the 67 years, why should we care? We will not be around to see it. No one will. The universe itself may not exist in any recognizable form by the time the first stellar black holes complete their transitions. But physics is not always about what we can observe. Sometimes it is about what is true, whether or not we are there to see it. And the bounce, if it is real, changes our understanding of what happens inside black holes, regardless of when the outside world sees the result. There is another way to think about the timescale, one that brings it back towards something almost tangible. The bounce from the outside looks like Hawking evaporation. It looks like a slow, steady loss of mass as radiation drifts away from the black hole's event horizon. Hawking radiation is one of the great discoveries of 20th century physics. Stephen Hawking showed in 1974 that black holes are not perfectly black. They emit a faint glow of particles created by quantum effects at the event horizon. The radiation is incredibly weak. A stellar mass black hole has a Hawking temperature of about 1/1000th of a degree above absolute zero, but it is real. It carries energy away from the black hole, and by the equivalence of mass and energy, it causes the black hole to lose mass. Over time, the black hole shrinks. Eventually, after that unimaginably long timescale, it shrinks to nothing and disappears. Or does it? The standard picture of Hawking evaporation assumes that the black hole simply radiates away until it is gone. But there is a famous problem with this picture, a problem that has tortured theoretical physicists for 50 years. It is called the black hole information paradox. The paradox goes like this. When matter falls into a black hole, it carries information with it. Information about what it was made of, how it was arranged, its entire quantum state. In quantum mechanics, information is never lost. It can be scrambled, mixed up, made practically inaccessible, but it is always there in principle. This is a deep feature of the theory, one that underlies the reversibility of physical laws. But Hawking radiation appears to be thermal. It is random, featureless, carrying no information about what fell into the black hole. If the black hole evaporates completely, and all that remains is this thermal radiation, then the information that fell in has been destroyed. The quantum state of the infalling matter has been erased, and that violates the fundamental principles of quantum mechanics. Physicists have proposed many solutions to this paradox. Some say the information is encoded subtly in the Hawking radiation. Some say it is stored in a remnant that survives the evaporation. Some say it escapes through wormholes, or is preserved in some other exotic structure. The debate has been fierce and is not yet settled. But the black-to-white hole bounce offers a different resolution. If the black hole does not evaporate completely, if instead the infalling matter bounces and emerges through a white hole, then the information is never lost. It goes in, passes through the quantum bridge, and comes out the other side. The Hawking radiation we see from outside is not the whole story. It is a kind of optical illusion, a consequence of the extreme time dilation. The real story is the bounce, and the bounce preserves everything. This is elegant if it is true. It solves the information paradox without requiring exotic new physics or implausible coincidences. The information survives because the singularity does not form. The matter does not disappear, it transforms. Now let us hold this picture in mind and ask what it might mean for the origin of our own universe. If a collapsing star can bounce and produce a white hole, then what happened at the Big Bang? The Big Bang, as usually described, is a singularity in reverse. Space-time began from a point of infinite density. Everything in the universe, all the matter, all the energy, all the structure, emerged from that point. But the same objection applies. Infinite density is not physics. It is a breakdown of physics. A complete theory should explain what happened there, not throw up its hands and declare the question off limits. The idea that we have been circling is this. The Big Bang may be the white hole side of a bounce. Not a bounce that happened inside a star in our universe, but a bounce that happened inside a black hole in some other universe. From inside, the bounce looks like an explosion, matter expanding outward, space stretching, density decreasing. That is exactly what the Big Bang looks like. That is exactly what we observe when we look at the cosmic microwave background, the relic radiation from the hot, dense early universe. If this is correct, then our universe is the interior of a black hole in a larger cosmos. The event horizon that separated the black hole from its parent universe is, in a sense, our boundary. We cannot see past it. We cannot send signals through it. From our perspective, it is not a horizon at all. It is simply the edge of everything, the place where our measurements run out. But from the perspective of the parent universe, there is a black hole, and inside that black hole a new cosmos has been born. Picture an infinite tower of nested realities. Each universe contains black holes. Each black hole contains a universe. The chain extends upward and downward without end. There is no base, no ceiling, no final floor. Just levels within levels, each one as real as the others, each one containing minds and stars and galaxies and questions. We cannot see the parent universe. We cannot measure it, detect it, or interact with it in any direct way, but we might be able to see its shadow. This is where the observational signatures begin to matter. If the bounce picture is correct, it should leave traces, not obvious ones. We are talking about effects from the Planck scale, imprinted on a universe 14 billion years old and nearly 100 billion light-years across, but traces nonetheless. The first place to look is the cosmic microwave background. The CMB is a map of the universe as it was about 400,000 years after the Big Bang. When the primordial plasma cooled enough for light to travel freely, it is astonishingly uniform. The temperature varies by only about 1 part in 100,000 across the entire sky. But those tiny variations are not random. They carry information about the physics of the early universe. If our universe bounced, the bounce might leave an imprint on the CMB. The quantum fluctuations that seeded the variations in temperature would have passed through the Planck scale transition, and that passage might distort them in characteristic ways. Some models predict a slight suppression of fluctuations on the larger scales. Others predict subtle asymmetries, correlations that break the statistical isotropy we expect from a simple inflationary expansion. In fact, anomalies like this have been observed. The CMB has a cold spot, a region of the sky that is slightly cooler than expected. It has a hemispherical asymmetry. One half of the sky is slightly different from the other. It has a lack of power on the larger scales. The biggest fluctuations are smaller than they should be according to the standard model. These anomalies are puzzling. They are not large enough to overthrow the standard picture, but they are persistent, and they have resisted easy explanation. Are they traces of the bounce? Perhaps. The honest answer is that we do not know. The anomalies could be statistical flukes. They could be artifacts of our analysis methods. They could be signs of new physics that has nothing to do with quantum gravity. But they are exactly the kind of signal we would look for if we wanted to test the bounce hypothesis. They are hints, not proof. They are reasons to keep looking. The second place to look is the sky at high energies. If primordial black holes formed in the early universe, not from collapsing stars, are completing their bounces today, they might be detectable. A white hole burst, the moment when the trapped matter finally emerges, would release energy. A lot of energy. The exact spectrum and intensity depend on the mass of the original black hole and the details of the bounce, but some models predict bursts in the gamma ray or radio spectrum that would be brief, intense and distinctive. We have not seen such bursts with certainty. Gamma ray astronomy is difficult. The sky is full of transient events, and distinguishing a white hole burst from a distant supernova or a neutron star collision is not straightforward. But the search is ongoing. Telescopes like Fermi and Cherenkov arrays are watching the sky, cataloguing every flash, building up statistics that might, one day, reveal an excess of events that cannot be explained by known astrophysics. There is also gravitational wave astronomy. The merger of two black holes produces ripples in space-time that we can detect with instruments like LIGO and Virgo. If the black holes involved are not true singularities but bouncing objects with Planck-scale cores, the gravitational wave signal might differ from the predictions of classical general relativity. The differences would be subtle. A slight change in the ring-down phase, a modification to the expected spectrum, but they might be measurable as our detectors improve. None of these tests is conclusive. None of them has yet provided definitive evidence for or against the bounce picture. But that is the nature of frontier physics. The ideas come first, the technology catches up, and eventually, if the ideas are correct, nature reveals itself. Let us dwell for a moment on what it would mean if these signatures were found. Imagine that a future telescope detects a pattern of gamma-ray bursts that matches the predicted signature of white hole events. Imagine that the distribution of burst energies corresponds to the masses of primordial black holes that should have formed in the early universe. Imagine that no other astrophysical process can explain the data. It would not be a discovery of a new planet or a new particle. It would be a discovery about the structure of space-time itself. It would tell us that singularities do not exist, that the collapse of matter is not the end, that the universe has depths within depths that we have only begun to suspect. It would tell us that the Big Bang was not a beginning, but a transition, not a creation, but a passage. It would tell us that the story of existence is longer, stranger, and more connected than we ever imagined. Or imagine that the anomalies in the cosmic microwave background are explained, and the explanation involves a bounce. Imagine that the suppression of large-scale power, the cold spot, the hemispherical asymmetry, all fall into place as natural consequences of a Planck-scale transition at the start of the universe. It would be like finding a fossil in the sky, a trace of the moment before time as we know it began. These are possibilities, not certainties. The mathematics is there, the predictions are being made, the observations are being planned, but nature has the final word, and nature has not yet spoken clearly. For now, rest with the picture we have assembled. A black hole forms, matter falls inward. The collapse reaches the Planck scale and stops, not because of any external force, but because space-time itself resists further compression. The matter bounces. It emerges eventually as a white hole, a fountain of energy and information pouring out of a region that was once a drain. From outside, the process takes unimaginable eons. From inside, it is over before it begins, and the Big Bang, the origin of everything we can see and touch and measure, may be exactly such a bounce, viewed from the inside. The parent universe is hidden from us, separated by a horizon we call the edge of the observable cosmos. We cannot go back, we cannot look through, but we are here because something fell and something bounced, and we are what emerged. The night sky is quiet. The stars burn in their solitude. But beneath the stillness, the mathematics suggests a structure deeper than we see, a chain of universes linked by collapse and rebirth, each one the child of a black hole in the one before. Whether this is true remains an open question, one that the next generation of telescopes and theorists will address. But the question itself is extraordinary, and the willingness to ask it, to follow the equations wherever they lead, to take seriously the possibility that the universe is not what it seems, is the heart of what physics does. Now let that settle. Let the scale of it rest in your mind, and when you are ready, we will go further still. We have spoken of collapse, of bounce, of the possibility that our universe emerged from the interior of a black hole in some larger realm. But there is a question that rises naturally from all of this, a question that any careful listener will have formed by now. If the bounce happens, if matter really does fall through the Planck scale and emerge somewhere else, what happens to the information that went in? What happens to the history encoded in every atom, every photon, every quantum state that crossed the horizon? This is not an idle concern. It is in fact one of the deepest problems in all of physics, the black hole information paradox. And any proposal that claims to describe what happens inside a black hole must eventually face it. Let's take a moment to understand what the problem actually is. When something falls into a black hole, it seems to disappear from the universe. Its mass adds to the black hole's total. Its charge, if it has any, adds to the black hole's charge. Its angular momentum adds to the black hole's spin. But everything else, every detail of what it was, where it came from, how its atoms were arranged, appears to be erased. The black hole, as described by classical general relativity, has no hair. It is characterized entirely by three numbers: mass, charge, spin. Two black holes of the same mass, charge, and spin are identical, regardless of whether one was made from a collapsing star and the other from a collapsing cloud of antimatter. The information is gone. But quantum mechanics does not allow information to be destroyed. This is not a preference or a convention. It is built into the structure of the theory at the deepest level. The evolution of a quantum system is described by something called a unitary operator, and unitarity is another word for reversibility. In principle, if you know the final state of a system, you can run the equations backward and recover the initial state. Nothing is lost. Nothing is created from nothing. The total amount of information in a closed system is conserved. So when a black hole forms and matter falls in, quantum mechanics says the information must still exist somewhere. And when the black hole evaporates through Hawking radiation, as Stephen Hawking showed it must, the information must come out. But Hawking's original calculation suggested that the radiation is thermal, pure random noise carrying no information at all. The black hole would evaporate completely, and the information that fell in would be gone forever. This is the paradox. Either quantum mechanics is wrong, or general relativity is wrong, or there is something about black holes that neither theory fully captures. For decades, physicists have struggled with this problem. Various solutions have been proposed. Perhaps the information is somehow encoded in the Hawking radiation in ways too subtle for the original calculation to capture. Perhaps it leaks out slowly, spread across the radiation in delicate correlations. Perhaps it is stored in a remnant left behind after the evaporation, a tiny Planck-scale nugget that remembers everything. Perhaps the information escapes through wormholes, or is duplicated at the horizon, or is projected onto the boundary of space-time in a holographic encoding. The bounce picture offers its own answer, and it is an elegant one. If the black hole does not end in a singularity but instead bounces and becomes a white hole, then the information that fell in is not destroyed. It emerges on the other side. The interior of the black hole becomes the interior of a white hole, and everything that went in eventually comes out, not as Hawking radiation, but as the original matter, transformed and delayed but fundamentally intact. The universe forgets nothing. The apparent loss of information is an illusion created by the enormous time dilation near the horizon. From outside, you cannot recover the information because you cannot wait long enough, but the information is there, stored in the deep interior, waiting to emerge when the bounce is complete. This is a satisfying resolution, but it raises its own questions. If the bounce takes as long as Hawking evaporation when viewed from outside, does the information come out through the Hawking radiation or through the white hole emergence? How do these two processes interact? Is there a moment when both are happening simultaneously, or does one smoothly transition into the other? These are active areas of research, and the answers are not yet clear. But the key insight is that the bounce provides a mechanism for information preservation that does not require exotic physics beyond quantum gravity itself. The unitarity of quantum mechanics is maintained. The laws of physics are not violated. The information is simply taking the long way around. Consider what this means for the black hole at the centre of our galaxy, the one called Sagittarius A yield, with its 4 million solar masses and its dark presence bending the orbits of nearby stars. If the bounce picture is correct, then everything that has fallen into Sagittarius A over the past billions of years, gas clouds, wandering planets, unlucky stars, perhaps entire civilizations, is not gone. It is stored in the deep interior, in a region of space-time that is causally disconnected from us, inaccessible to any observation we can make. But it exists, it remembers, and eventually on timescales that make the current age of the universe look like the blink of an eye, it will emerge, not as it was perhaps, transformed by the passage through the Planck scale, reconfigured by the bounce, but fundamentally intact. The history is not lost, and here is where the picture connects back to it. And every black hole that forms in our universe, if the picture is correct, is the seed of another universe, another interior, another set of emerged beings who will one day look up at their sky and wonder where they came from. This is the chain of cosmic inheritance that the mathematics suggests. It is not proven. It may never be provable in the usual sense, but it is consistent, it is elegant, and it solves problems that have puzzled physicists for decades. The information paradox dissolves, the singularity is avoided, the Big Bang is explained, and the price is accepting that the universe is far larger and stranger than we see. Now let us go deeper into the mathematics of the white hole, because there is a subtlety here that is easy to miss. When we say that a white hole is the time reverse of a black hole, we are making a statement about the equations, not about the physics. The equations of general relativity are symmetric under time reversal. If a solution exists that describes matter falling inward and never escaping, there must also be a solution that describes matter shooting outward and never returning. But this mathematical symmetry does not mean that both solutions are equally likely to be realized in nature. In everyday experience, time has a direction. Eggs break but do not unbreak. Coffee cools but does not spontaneously heat. The universe evolves from lower entropy to higher entropy, from simpler states to more complex ones. This arrow of time is built into thermodynamics, and it suggests that white holes, which would require matter to emerge from nothing, to decrease in entropy, to reverse the normal flow of causation, should not exist. And yet the bounce picture says they must. How do we reconcile this? The answer lies in the Planck scale transition. At everyday scales, the arrow of time is clear. At the scales of quantum gravity, something different may happen. The very notion of time may break down at the Planck scale. Before and after may cease to be meaningful. The bounce is not a process that happens in time. It is a transition that connects two regimes of time, one in which matter is falling inward and one in which matter is flowing outward. From the perspective of an observer watching from far away, the transition takes an enormous amount of time. Long enough for the black hole to evaporate through Hawking radiation, long enough for trillions of years to pass. But from the perspective of matter falling through, there is no delay at all. The inward flow connects smoothly to the outward flow. The thermodynamic arrow of time, which depends on the flow of entropy in a given region, does not prevent the transition. because the transition happens at a scale where entropy itself may not be well defined. This is speculative. This is the edge of what the current theory can tell us. But it is important to understand that the emergence of white holes from black holes is not a violation of thermodynamics in the usual sense. It is a quantum gravitational process that connects two thermodynamically sensible regimes, the collapse and the expansion, through a domain where the usual rules do not apply. The arrow of time is preserved on both sides of the bounce. It simply points in different directions relative to the external universe. Let that settle. Now consider the cosmological implications more carefully. If our universe is the interior of a black hole, then the Big Bang was not a moment of creation. It was a moment of arrival. Matter from the parent universe, compressed to infinite density in the classical picture, but merely to Planck density in the quantum picture, emerged into a new interior space-time. The extreme conditions of the early universe, the temperatures of trillions of degrees, the densities far beyond anything found in nature today, the primordial plasma of quarks and gluons, were the immediate aftermath of the bounce. The universe inflated, cooled, and began the long process of structure formation that eventually led to galaxies, stars, planets, and life. But there is a prediction here, a subtle one, that connects to observations we have already made. In the standard picture of cosmology, the Big Bang is followed by a period of inflation, a rapid exponential expansion driven by a hypothetical field called the inflaton. Inflation solves several problems. It explains why the universe is so flat, why it is so uniform, why the cosmic microwave background looks the same in every direction. But inflation requires fine-tuning. The inflaton field must have just the right properties, the initial conditions must be just right, the exit from inflation must happen in just the right way. Physicists have always been uncomfortable with this. It works, but it feels contrived. The bounce cosmology offers an alternative. If the universe emerged from a black hole bounce, the extreme conditions at the Planck scale may naturally produce the kind of expansion that inflation requires. The torsion in space-time, a feature of Popowski's approach that does not exist in standard general relativity, acts as a kind of cosmic spring. It pushes matter apart at the moment of the bounce, driving a rapid expansion that mimics inflation without requiring a separate inflaton field. The flatness and uniformity of the universe are explained not by a special field, but by the generic physics of the bounce itself. This is not yet proven. The calculations are difficult and the predictions are subtle. But it suggests that the bounce picture is not just a philosophical curiosity. It has testable consequences that may distinguish it from the standard model of cosmology. If inflation is replaced by a bounce-driven expansion, the spectrum of primordial fluctuations may be different. The pattern of hot and cold spots in the cosmic microwave background may carry traces of the bounce dynamics. The gravitational waves produced in the early universe may have different frequencies and amplitudes than inflation predicts. These are signatures that future experiments may detect. The next generation of cosmic microwave background observatories, the next generation of gravitational wave detectors, the next generation of space telescopes, all of them will be sensitive to effects that could reveal the nature of the early universe. If the bounce picture is correct, the evidence may already be encoded in the sky, waiting for instruments sensitive enough to read it. And here is a thought worth holding. We have been treating the bounce as a single event, a unique transition at the beginning of our universe. But if every black hole gives rise to a new interior, if every collapse is followed by a bounce, then the cosmos is not a single universe, but a tree of universes, an endless branching structure of interiors within interiors, each one the child of a black hole in the one before. The parent universe that gave birth to ours may itself have emerged from a bounce, and the parent of that parent, and the parent of that, extending backward in a chain that may have no first member. This is not time as we usually think of it. The parent universes are not in our past in the sense that yesterday is in our past. They are causally disconnected from us, existing in their own space-times, evolving according to their own histories, but they are linked to us through the structure of space-time itself, through the black holes that serve as the bridges between one interior and another. We cannot visit them, we cannot communicate with them, but we are made of what came through, and what we do here, the black holes we form, the matter we compress, the structures we build, may seed the interiors of universes yet to come. Let that rest in your mind, let the scale of it settle. There is a kind of cosmic ecology here, a picture of existence in which universes are not created and destroyed but transform, one into another, through the universal process of gravitational collapse and quantum bounce. The matter is never lost, the information is never erased, it simply moves from one interior to another, carrying structure and complexity and the potential for new forms of organization. And life? What role does life play in this picture? This is perhaps the most speculative question of all, and the mathematics does not answer it. But we can observe that life is a process that organizes matter, that creates complexity, that stores and manipulates information. If information is conserved through the bounce, if the complexity built up in one universe can influence the structure of the next, then there is at least the possibility that what we do matters beyond the horizon of our own cosmos. This is not a scientific claim. It is a philosophical implication, drawn loosely from the physics but not derived rigorously. The equations describe the geometry of space-time, not the meaning of existence. But the picture suggests a kind of connectedness, a sense that the universe is not isolated, not singular, not bounded by the darkness we see at the edge of our sky. There is something beyond. There was something before, and there will be something after, long after our sun has faded and our galaxy has drifted into the void. The night is quiet now. The mathematics has carried us far from where we began. From black holes to white holes, from collapse to bounce, from singularities to Planck-scale transitions, from isolated stellar objects to chains of universes linked by gravitational inheritance. The questions remain open. The observations have not yet confirmed or refuted the picture, but the questions themselves are profound, and the willingness to ask them, to follow the equations into domains where intuition fails, to take seriously possibilities that would have seemed absurd a century ago, is the deepest expression of what it means to do physics. Rest here for a moment. Let the ideas settle into silence, and when you are ready, we will continue, further still, into the implications of this strange and beautiful possibility. The silence between universes is not empty. It is structured. It has geometry, curvature, a shape that the mathematics can describe even if the imagination struggles to picture it. And within that silence, within the Planck-scale foam, where one cosmos ends and another begins, there is a question that presses against everything we have considered so far. How would we know? How would we know if this picture is true? How would we know if our universe really did emerge from the interior of a black hole in a parent cosmos? If the Big Bang was not a beginning but a transition? If the singularity that our theories predict was replaced by a quantum bounce that carried information from one side to the other? This is not a rhetorical question. It is the question that separates physics from philosophy, that distinguishes a beautiful idea from a testable theory. And the remarkable thing, the thing that makes this line of research more than speculation, is that there are answers. Not definitive answers, not yet, but pathways, signatures, fingerprints that the bounce might have left on our cosmos, faint traces that the next generation of instruments might be able to detect. Let us begin with the most direct signature, the one that connects most immediately to the black-to-white hole transition we explored earlier. If stellar black holes undergo quantum bounces, if the matter that falls in eventually re-emerges as a white hole, then the universe should contain white holes. Not in the far future, not in some abstract theoretical limit, but now, today, drifting through the cosmos, the remnants of black holes that formed long ago and have completed their transitions. The question is, what would they look like? The answer depends on timescales. Remember that the bounce, from the perspective of the infalling matter, happens quickly, essentially instantaneously on human terms. But from the perspective of an outside observer, the transition is stretched by the extreme time dilation near the horizon. A black hole that forms from a collapsing star takes an extraordinarily long time, by external clocks, to complete its transition to a white hole. The calculations are delicate, and different models give different numbers, but the order of magnitude is set by the mass of the black hole and the fundamental constants of nature. For a stellar mass black hole, something 10 or 20 times the mass of our Sun, the bounce time is enormous. Longer than the current age of the universe. Longer in some models than the timescale of proton decay, if protons decay at all. These objects have not yet bounced. They are still in the slow-motion process of transitioning. frozen from our perspective at the edge of the horizon, waiting for cosmic time to catch up with the quantum process unfolding in their interiors. But there is another population of black holes, a population that may be far more numerous and far more relevant to the question of observational signatures. These are the primordial black holes, the objects that may have formed not from collapsing stars but from density fluctuations in the early universe in the first fraction of a second after the Big Bang. The key difference is their mass. Primordial black holes could have formed across an enormous range of masses, from the Planck scale, impossibly tiny, smaller than a proton by a factor of a trillion, all the way up to thousands or millions of solar masses, and the smaller the black hole, the shorter the bounce time. Here is where the numbers become interesting. A primordial black hole with a mass of around 100 million metric tons, roughly the mass of a small asteroid, compressed into a space smaller than an atomic nucleus, would have a bounce time comparable to the current age of the universe. These objects, if they formed in the early cosmos, would be completing their transitions now. They would be becoming white holes in our epoch, in our sky, perhaps in our galactic neighbourhood. What would that look like? The mathematics predicts an explosion, not a gentle fading, not a slow leak of energy, but a sudden, violent release of all the matter and energy that fell into the black hole over its lifetime, compressed and processed and ejected in a burst of radiation. The spectrum of this radiation is still a matter of active research, but the models suggest it would peak at high energies, gamma rays, possibly even higher. A flash of light, appearing suddenly in the sky, lasting perhaps a fraction of a second, carrying the integrated energy of everything the black hole ever consumed. This sounds familiar. It sounds very much like a gamma ray burst, one of the most energetic phenomena we observe in the cosmos. And indeed there is active research exploring whether some observed gamma ray bursts, particularly the short, hard bursts that do not fit neatly into the standard categories, might be the signatures of primordial black hole bounces. The connection is not yet established, the theoretical predictions are not yet precise enough, and the observational data are not yet discriminating enough to make a definitive identification. But the possibility is real. The next generation of gamma-ray telescopes, the next survey of transient phenomena in the high-energy sky, might detect something that does not match any known astrophysical source. And if it does, if the spectrum and duration and statistics match the predictions of the bounce models, we would have evidence, not proof, but evidence, that the black-to-white hole transition is not just a mathematical possibility, but a physical reality. Let this settle for a moment. The idea that we might detect in the burst of light from a distant point in space the echo of a process that began before the first stars formed, that connects to the deeper structure of quantum gravity, that validates or falsifies a picture in which our entire universe is the interior of a black hole. This is not science fiction. This is observational astronomy, pushed to its limits, reaching for signatures that would tell us something about the nature of space-time itself. But there is another signature, one that is in some ways even more profound, because it would speak not to the fate of small primordial black holes, but to the origin of our own cosmos. If our universe really did emerge from a bounce, if the Big Bang was the white hole transition from a parent black hole, then the conditions at the moment of the emergence were not arbitrary. They were set by the physics of the bounce, by the geometry of the transition, by the way quantum gravity smooths and restructures the Planck scale dynamics. And those conditions should have left traces, not in the distribution of galaxies or the chemistry of stars. Those are processes that came much later, shaped by astrophysics rather than quantum gravity. But in the very first light, in the afterglow of creation, in the cosmic microwave background radiation that fills all of space and carries information from the earliest moments of the universe. The cosmic microwave background is a photograph of the universe when it was about 380,000 years old, when the primordial plasma cooled enough for atoms to form and light to travel freely for the first time. This light has been travelling ever since, stretched by the expansion of space from visible to microwave wavelengths, carrying the imprint of the conditions that prevailed in that early epoch. We have mapped this light with exquisite precision, using satellites like COBE and WMAP and Planck, measuring its temperature and polarization across the entire sky to an accuracy of parts per million. And what we see is almost perfectly uniform, a glow with the same temperature in every direction, to better than 1 part in 10,000, almost. The almost is where the interesting physics lives. There are tiny fluctuations, ripples in the temperature from place to place, reflecting variations in the density of matter in the early universe. These fluctuations are the seeds of all cosmic structure. The places where matter was slightly denser became the galaxies and clusters and filaments we see today. The places where matter was slightly thinner became the voids. The statistics of these fluctuations, their amplitudes, their correlations across different angular scales, their patterns of hot and cold spots, encode information about the physics of the early universe. And if that physics included a bounce, if the Big Bang was a transition from a prior state rather than a beginning from nothing, then the fluctuation should carry the signature of that transition. What kind of signature? This is where the research becomes technical, and different models make different predictions. But one generic feature of bounce cosmologies is that they naturally produce fluctuations with a characteristic spectrum, one that is almost but not quite scale invariant, meaning the fluctuations have nearly the same amplitude on all scales, but with small deviations that encode the details of the bounce dynamics. Standard inflationary cosmology also produces nearly scale-invariant fluctuations, so the mere existence of this pattern does not distinguish between the two pictures. The distinction lies in the details, in the precise shape of the spectrum, in the statistical properties of the fluctuations, in the presence or absence of specific features that one model predicts and the other does not. One such feature is a particular kind of asymmetry. Standard cosmology assumes that the fluctuations are statistically isotropic. They have the same properties in every direction, reflecting the uniformity of the physical laws that generated them. But bounce cosmologies, particularly those in which our universe emerged from a rotating black hole or from a bounce that broke spatial symmetry in some subtle way, might produce fluctuations that are slightly asymmetric. There would be a preferred direction in the universe, a subtle alignment of the hot and cold spots, a breaking of the perfect isotropy that standard models predict. And here is the remarkable thing. The data may already show hints of this. When the Planck satellite measured the cosmic microwave background with unprecedented precision, the team found several anomalies, statistical oddities that do not quite fit the standard cosmological model. One is a hemispherical asymmetry, a slight difference in the amplitude of fluctuations between one half of the sky and the other. Another is an unusual alignment of the larger scale fluctuations, the so-called axis of evil, a pattern that appears unlikely to arise by chance. These anomalies are not statistically overwhelming. They hover at the edge of significance, tantalizing but not definitive. They could be flukes, statistical accidents in a universe that is fundamentally isotropic. Or they could be the first faint traces of something deeper, the fingerprints of a bounce that left our cosmos slightly marked, slightly asymmetric, slightly different from the perfect uniformity that standard models predict. The research continues, new observations are planned, future missions will map the cosmic microwave background with even greater precision, measuring not just the temperature but the polarization, searching for the subtle patterns that different theories predict. And if the anomalies persist, if they grow more significant with better data, if they match the predictions of specific bounce models, then we would have evidence, encoded in the oldest light in the universe, that our cosmos did not begin from nothing, that it emerged from something, that the Big Bang was a transition and there was a before. Let this rest in your mind. The idea that the very first light, the ancient glow that fills all of space, might carry information about whether we live inside a black hole. This is where theoretical physics meets observational cosmology, where the most abstract ideas about quantum gravity connect to the most precise measurements of the real sky. The connection is fragile, the signatures are subtle, but they are there to be searched for, and the searching is underway. There is yet another signature, one that looks not outward to the sky but inward to the fabric of space itself. If our universe emerged from a bounce, if the quantum corrections that prevent singularities left an imprint on the structure of space-time, then that imprint might be visible in the geometry of gravitational waves. These are ripples in space-time propagating outward from violent events like the mergers of black holes and neutron stars. We have detected them, beginning in 2015 with the LIGO experiment, and we have learned to read their waveforms, extracting information about the masses and spins and distances of the objects that produced them. The gravitational wave sky is now open to us, a new window on the cosmos complementary to light and particles and all the other messengers we have used before. The standard theory, general relativity, Einstein's equations, makes precise predictions for what these waveforms should look like, and so far the observations match. But loop quantum gravity, the framework that underlies the bounce models, makes slightly different predictions. The quantum corrections that smooth the singularity also modify the dynamics of black holes in subtle ways, changing the way they ring when they merge, altering the fine details of the gravitational waves they emit. These modifications are small, suppressed by the Planck scale, which is so far below the scales we can probe directly. But there are hopes, tentative, speculative, but grounded in real calculations, that the next generation of gravitational wave detectors might be sensitive enough to see the difference, that the waveform from a black hole merger might carry, encoded in its fine structure, the signature of quantum gravity at work. This is not something we can detect today. The current instruments are not precise enough, and the theoretical predictions are not complete enough to make a definitive test. But the technology improves, the calculations sharpen. The next generation of detectors, LISA in space, the Einstein telescope on the ground, the cosmic explorer proposed for the deserts of the American Southwest, will be orders of magnitude more sensitive than what we have now. And if they see deviations from Einstein's predictions, deviations that match the predictions of loop quantum gravity, we would have evidence that spacetime itself is quantized at the smallest scales, that singularities do not form, that black holes bounce. Imagine for a moment what it would mean. You would open a scientific paper, or perhaps see a headline, announcing that the gravitational wave signature from a distant black hole merger does not match general relativity. That the ring down, the final vibration of the merged black hole settling into equilibrium, carries overtones that Einstein's equations did not predict. And buried in the analysis, in the comparison to different theoretical models, there would be a statement. The deviation is consistent with loop quantum gravity. The data favour a singularity-free model. The data suggest that black holes bounce. This has not happened. It may never happen. The universe may not cooperate. But the possibility is there, written into the mathematics, waiting for the instruments to catch up. And the researchers are watching, calculating, preparing for the day when the data might speak. Let this settle gently now. We have travelled far from the quiet geometry of collapsing stars, far from the simple image of a black hole as a point of no return. We have seen how quantum gravity might replace the singularity with a bounce, how the trapped region might eventually open into a white hole, how the timescales of this transition appear infinite from outside but finite from within. We have explored the possibility that our own universe is the interior of such a transition, that the Big Bang was not a beginning but a passage, that there may be a parent cosmos beyond the horizon of our observations. And we have seen that this picture, strange as it is, makes predictions. Predictions about primordial black hole explosions, about anomalies in the cosmic microwave background, about deviations in gravitational wave signals. The picture is not yet confirmed. It may never be confirmed, but it is not mere philosophy. It is physics, reaching toward the data, waiting to be tested. And yet, beneath all the equations and observations, there is a simpler question, one that does not require a telescope or a particle detector to feel. If this picture is true, if we live inside a black hole, if the Big Bang was a bounce, if the cosmos is part of an endless tree of universes growing from collapse after collapse, what does it mean? What does it mean for us, here, now, lying quiet in the dark, thinking about things so vast that the mind can barely hold them? The mathematics does not answer this. The physics describes the geometry, not the meaning. But there is something in the picture that resonates, something that speaks to the old human questions about origins and endings and the structure of existence. We're used to thinking of the universe as singular, unique, the one and only arena in which all of reality plays out. The bounce cosmologies suggest something different. They suggest that our universe is one of many, that creation is not a one-time event but an ongoing process, that the cosmos is fertile, productive, always giving birth to new regions of space-time through the gravitational collapses that occur within it. There is something almost biological in this picture, something that echoes the way life propagates, generating new individuals from the bodies of the old, and there is something consoling in it as well. In standard cosmology, the long-term future is bleak. The universe expands forever, the stars burn out, the The galaxies drift apart and eventually all structure dissolves into a thin haze of particles, growing ever colder, ever emptier, ever more alone. This is the heat death, the final equilibrium, the end of all process and change. But if black holes bounce, if the matter that falls in eventually emerges somewhere else, in a new interior, in a new cosmos, then the story does not end. It transforms. The matter we are made of, the atoms in your body and the light in your eyes, may eventually fall into a black hole, may eventually pass through a bounce, may eventually become part of a universe yet to be born. The loss is not final. The darkness is not permanent. There is always another interior, another transition, another beginning. This is not a promise. It is a possibility, drawn loosely from equations that are not yet fully understood, from models that are not yet fully tested. But it is a possibility that changes the shape of the darkness, that softens the hard edge of cosmic fate. And sometimes, when the night is quiet and the stars seem very far away, a softening of the darkness is enough. Rest here for a moment. Let the scale of it settle. The night is patient. The universe is old. And the questions we carry about what came before, about what lies beyond, about the meaning of our small presence in this vast and strange cosmos, these questions will still be there when we wake. For now, let them wait. Let the mathematics hold its secrets a little longer, and when you are ready, we will continue further into the quiet heart of these strange and beautiful ideas. The darkness you're resting inside, the one that wraps around this room, around your body, around the breath you are taking now, is a kind of boundary, not a wall, but a threshold. And thresholds, as we have learned, are where the strangest transformations happen. The horizon of a black hole is a threshold. The bounce at the heart of a collapse is a threshold. The moment of the Big Bang, if the bounce cosmologies are right, was a threshold too. Not a beginning from nothing, but a passage from something else. A crossing over from one kind of geometry into another. And now, we're going to spend some time on that passage. We're going to linger at the threshold itself and ask what it would actually be like to cross it. Not the mathematics of it. We have walked through that already. The spin networks and the repulsive quantum pressure and the tunneling amplitudes. But something more immediate, more visceral. If you were there, if you were somehow present at the moment of the bounce, what would you experience? What would you see? The honest answer is that we do not know. The equations describe the geometry, but they do not describe experience. They tell us how space-time curves and what the density of matter does, and how the quantum corrections prevent the singularity, but they do not tell us what it feels like to be a particle passing through the transition, or an observer, if such a thing could exist, watching the geometry invert around them. But we can guess. We can use the mathematics as a scaffold and imagine our way into the picture, and the guessing is itself a kind of understanding, a way of making the abstract feel real, even if only for a moment. So imagine this. You are falling. You've been falling for a long time. So long that the word time has started to lose its meaning. The space around you is curved so steeply that light itself bends and twists, and the stars you once saw above you have compressed into a bright ring, a halo of photons caught in the last stable orbit before the horizon. You crossed that horizon some time ago, though you did not feel it. From the outside, your crossing would have looked like a freeze, a smear, an image of you slowing and dimming at the edge of the visible forever. But from the inside, you felt nothing special. You kept falling. Now the density is rising. The matter around you, if there were matter around you, would be squeezed tighter and tighter, the atoms crushed into each other, the nuclei overlapping, the quarks themselves pressed into a soup of interacting fields. In the classical picture, the picture Einstein painted, this compression goes on forever. The density rises without limit. The curvature grows without bound. You are approaching the singularity, the point of infinite density, the place where the equations break and physics holds up its hands and admits it does not know what happens next. But in the quantum picture, something different occurs. As the density approaches the Planck scale, the quantum corrections become large. The discrete structure of space-time, the granularity of the spin networks, begins to resist further compression. The falling slows, not because of any force you can feel, but because the geometry itself is stiffening. And then, at some critical point, at a density roughly 10 to the 94 grams per cubic centimetre, a number so large that writing it out would fill a page with zeros, the curvature reaches its maximum, the falling stops, and reverses. This is the bounce. From your perspective inside, the reversal is instantaneous. There is no pause, no moment of hanging at the turning point, no experience of waiting. One moment you're falling inward, the next you're expanding outward, and the transition between them takes no time at all. It is like the tip of a pendulum swing, the instant where all the motion is potential, stored in position rather than velocity, and then released in the opposite direction. You pass through the bounce without knowing you have done it, without feeling anything change, and suddenly you're in a white hole, and the geometry around you is pushing outward instead of pulling inward. What do you see? That's harder to say. The light that fell in with you, the photons that crossed the horizon beside you, they are bouncing too. They are expanding outward with you, and if you could look at them, if your eyes or your instruments could still function at Planck densities, you would see them blue shifting as they compress and then red shifting as they expand. You would see the universe you left behind, the parent universe, the one with the collapsing star receding behind you, growing smaller and fainter, and you would see a new space opening ahead, a new interior, the white hole geometry blooming outward from the bounce like a flower opening in slow motion, except it is not slow. From your perspective, it is instantaneous. From the perspective of someone still in the parent universe, watching from a safe distance as the black hole ages and evaporates, it takes as long as the Hawking evaporation time. Billions of years for a solar mass black hole, cosmological ages for the supermassive ones. But from your perspective, you cross the bounce in no time at all. This is the strange inversion we talked about earlier, the way the black hole interior and the white hole interior are connected through a region where time and space trade rolls, and it is the reason why the bounce cosmologies are so hard to test directly. The people inside, if there were people inside, if anything could survive the passage, would experience the transition instantly. The people outside would have to wait for eons. The two perspectives do not line up. The two clocks do not agree. And the boundary between them is not a place you can stand and look both ways. Let that settle. The mathematics says this is consistent. The equations do not forbid this kind of structure. The loop quantum gravity calculations suggest that the bounce is not just possible but inevitable, that any collapsing matter must eventually re-expand, that the singularity is replaced by a smooth transition through the Planck regime. And the torsion cosmologies of Popowski say something similar, using different mathematical tools. The fermions inside the collapsing matter generate a repulsive effect that halts the collapse and triggers the expansion. Two different approaches, two different formalisms, arriving at the same qualitative picture. Collapse does not end in a singularity. Collapse ends in a new beginning. And here is where the picture becomes truly strange. If this is what happens inside a black hole, if the interior of a black hole is not a point of infinite density, but a new expanding region of space-time, then what is our universe? We have circled this question before, touched on it lightly, and now let us sit with it more fully. In the standard cosmological picture, our universe began with the Big Bang, a moment of infinite density and infinite temperature and infinite curvature, from which all of space and time expanded. The singularity at the beginning of time is the same kind of singularity that Einstein's equations predict at the center of a black hole, a place where the mathematics breaks, where the physics fails, where the question, what happened before, does not make sense because there was no before for anything to happen in. But if the bounce cosmologies are right, then singularities do not exist. They are artifacts of an incomplete theory, relics of ignoring the quantum structure of space-time. And if singularities do not exist, then the Big Bang was not a singularity. It was something else. It was a bounce. The same kind of bounce that happens at the heart of a collapsing star. The same kind of transition that connects a black hole interior to a white hole interior. The same kind of passage through the Planck regime that we just imagined ourselves falling through. In this picture, the Big Bang was the inside of a collapse. Somewhere, in some larger universe, some parent cosmos we have never seen and can never access, a black hole formed. Matter collapsed, density rose, the quantum corrections kicked in, and a bounce occurred. And the interior of that bounce, of the expanding white hole geometry that bloomed outward from the transition, is our universe. We are living inside someone else's black hole. Let me say that more carefully because the words can mislead. We are not inside a black hole in the sense of being trapped behind a horizon, about to fall into a singularity. The singularity is gone, the bounce replaced it. We are in the expanding phase, the phase after the bounce, the phase where space-time is getting larger rather than smaller, where matter is spreading out rather than crushing inward. We are in the interior, yes, but the interior is not a prison, it is a cosmos, and the horizon that bounds us, if there is a horizon, is not visible from inside. We cannot see the edge of our universe, the place where our space-time meets the parent space-time. That boundary, if it exists, is hidden from us by the geometry itself. We are inside a bubble, a region of space-time that is causally disconnected from whatever lies beyond. We can send no signals out. We can receive no signals in. The parent universe is as inaccessible to us as the other side of an event horizon, because in a very real sense, we are on the other side of an event horizon. This is not science fiction. This is a mathematical possibility, drawn from the equations of loop quantum gravity and torsion cosmology. The models do not prove that this is what happened. They do not show that our Big Bang was definitely a bounce inside a larger universe, but they show that such a scenario is consistent with the physics as we understand it. They show that the question, what came before the Big Bang, might have an answer after all. Not nothing, not a singularity, but another universe, one in which a black hole formed, one whose collapse became our birth. And if this happened once, it could happen many times. Every black hole in our universe, by the same logic, might contain a new universe in its interior. The supermassive black hole at the centre of our galaxy, 4,000,000 times the mass of the Sun. It might have a cosmos inside it. The stellar black holes scattered throughout the Milky Way, the remnants of massive stars that burned and collapsed. Each one might contain its own expanding space-time, its own matter, its own history. Even the primordial black holes, if they exist, the tiny ones formed in the early universe. They might contain pocket universes, microscopic cosmoses, realities smaller than a proton on the outside and billions of light years across on the inside. This is the picture we have been building toward. A tree of universes, branching downward and upward, each collapse giving birth to a new interior, each interior potentially giving birth to further collapses, an endless genealogy of space-times connected through their bounces. And you might wonder, can we test this? Can we ever know if we're inside a black hole, if the Big Bang was a bounce, if the tree of universes is real? The honest answer is, maybe. The signatures we discussed earlier, the primordial black hole bursts, the CMB anomalies, the gravitational wave deviations, these are tests of the bounce hypothesis in general. If we see them, they would confirm that quantum gravity prevents singularities, that bounces occur, that the picture we have been painting has some reality to it. But proving that our particular Big Bang was a bounce inside a parent black hole is harder. Much harder. The difficulty is that the parent universe is causally disconnected from us. No signal can pass through the bounce horizon. No light from the parent cosmos can reach our telescopes. No particles from the parent world can interact with our detectors. In a strict observational sense, the parent universe is forever hidden. But there are subtler possibilities. The properties of our universe, the particular values of the constants of nature, the initial conditions at the Big Bang, the large-scale structure of the cosmos, these might carry information about the bounce that created us. If the bounce conserves certain quantities, if the torsion of the fermions imprints a particular pattern on the expanding geometry, if the Planck scale physics leaves a characteristic fingerprint on the radiation that filled the early universe, then we might be able to read that fingerprint. We might be able to infer that we came from a bounce, even if we cannot directly observe the parent universe. This is speculative. It is at the edge of what the current models can predict. But it is not impossible, and the search for such signatures is already underway. Cosmologists are looking at the cosmic microwave background with new eyes, searching for anomalies that might betray a non-singular origin. Gravitational wave observatories are being built with sensitivities that might detect the echoes of quantum gravity effects. The physics is reaching toward the data, even if the data has not yet reached back. And there is something else, something harder to measure but no less real, the shift in perspective that these ideas create. If we live inside a black hole, if the Big Bang was a bounce, if the cosmos is part of an infinite tree of connected universes, then the universe is not the lonely singular thing we once imagined. It is part of a larger structure. It has a parent in some sense. It may have siblings, other universes born from other collapses, other bounces, other branches of the tree. And it may have children, the black holes within our universe, the collapses yet to come, the bounces yet to happen. We are not alone in the void. We are part of a family of geometries, a lineage of space-times, a web of connections that stretches backward to the parent universe and forward to the universes yet to be born. This is not a religious claim. It is not a statement of faith. It is a possibility suggested by the mathematics, a picture that emerges when you take quantum gravity seriously and follow it to its conclusions. The picture may be wrong. The equations may be missing something. The experiments may reveal that singularities are real after all, that the bounces do not happen, that the tree of universes is a fantasy. But for now, in this quiet moment, in this darkness that wraps around you like a boundary, the possibility is there, and there is something in it that resonates with the old intuitions, the old feelings, the old sense that we are part of something larger than ourselves. The universe is not a thing apart. It is nested. It is connected. It is the interior of a process that began elsewhere, and it may be the parent of processes that will begin here. Rest with that. The mathematics is strange. The numbers are large. The timescales are unimaginable. But the core of the idea is simple. Nothing truly ends. Everything transforms. The darkness that swallows also gives birth. Let your breath slow. Let the weight of your body press gently into whatever surface is holding you. The universe you're lying in, this vast, ancient, expanding cosmos, may itself be lying inside something larger. May itself be held by a geometry beyond its own horizon. May itself be the interior of a transition that happened in another time, another space, another world. And if that is true, then the darkness around you is not empty. It is full. It is thick with the structures that hold the structures that hold the structures. It is the inside of a nesting, a hierarchy of geometries, a chain of cosmoses linked by their collapses and their bounces. There is more to say. There are questions we have not yet asked, implications we have not yet drawn. The tree of universes suggests something about the nature of time, about the meaning of causation, about the strange loops that connect past and future across the boundaries of black hole horizons. And there are signatures still to discuss, tests still to propose, observations still to imagine. But that can wait. The night is patient, the mathematics will hold, and the picture we have built, this strange, beautiful, vertiginous picture of a cosmos nested inside a cosmos inside a cosmos, it is not going anywhere. It will still be there when the darkness lifts. For now, let the strangeness settle. Let the scale of it rest quietly at the edge of your thoughts, and know that whatever happens next, whatever the experiments show, whatever the equations eventually reveal, you have touched something real tonight. A question that reaches all the way down, a possibility that opens all the way up, a quiet hint that the universe is stranger and more connected than we ever imagined it could be. And yet there is one more thread to follow, one more quiet implication to draw out of the darkness before we let the picture rest. If our universe is the interior of a black hole, and if that black hole sits inside a parent universe, then something very strange follows about the nature of beginnings. Think back to the Big Bang, that moment of impossible density, impossible temperature, impossible curvature that we have always called the start of everything. In the standard picture, the Big Bang is a singularity. It is the edge of time. Before it, there is nothing, not even a before. The question, what happened before the Big Bang, is supposed to be meaningless. Like asking what is north of the North Pole, time itself starts at that moment, and asking about its antecedent is a category error. But in the picture we have been building tonight, that edge dissolves. The Big Bang is not a beginning, it is a transition. It is the moment when the collapsing matter in the parent universe reaches the Planck scale, when the quantum corrections overwhelm the classical geometry, when the inward fall becomes an outward expansion, when the bounce happens. From the perspective of the parent universe, a star collapsed, a black hole formed, the matter fell inward and vanished behind the horizon. From our perspective, from the perspective of the matter that fell, the collapse reached its maximum compression, the geometry flipped, and a new universe began to expand, the same event. Two descriptions. One, collapse and bounce, seen from inside as a Big Bang, seen from outside as the formation of an ordinary astrophysical black hole. This means the Big Bang has a cause, not a supernatural cause, not a first mover, not something outside physics, but an ordinary physical process. A star ran out of fuel. Its core collapsed. Gravity overwhelmed the pressure that held it up. The matter fell inward, faster and faster, denser and denser, until quantum gravity caught it. And in that catching, in that moment of maximum compression, our universe was born. The Big Bang was not the first event. It was the consequence of a prior event. It was the inside of someone else's collapse. Let that settle. There is something almost homely about this picture. The origin of everything, the beginning of space, the beginning of time, the beginning of all the galaxies and stars and planets and minds that would eventually emerge, was just a stellar death, a supernova, a collapse, a bounce. The most dramatic event in our entire history, the moment that made all subsequent moments possible, was, from the perspective of the parent universe, just another day, just another massive star reaching the end of its fuel, just another black hole forming in the cosmic night. We do not know where that star was. We do not know what kind of matter it was made of, what the physics of the parent universe was like, whether there were observers there to watch it die. We do not know if anyone noticed. Perhaps there was a civilization in the parent universe that tracked collapsing stars, that catalogued black holes, that wondered what happened inside them. Perhaps they saw our parent black hole form and thought nothing of it. Just another entry in the database, just another region of space swallowed by its own gravity. They could not have known that inside that horizon, a new cosmos was being born. They could not have seen the expansion, the cooling, the nucleosynthesis, the structure formation, the emergence of galaxies and stars and planets, and, eventually, minds. All of that was hidden from them, trapped behind the event horizon, inaccessible to any signal or observation they could make. We are invisible to our ancestors. The parent universe, if it exists, cannot see us. We are on the inside of a one-way door, a causal boundary, a horizon that no information can cross in the outward direction. We are orphans in a very specific sense. Born from a parent we can never contact. Descendants of a cosmos we can never observe. The connection is real, but it is also absolute. We carry the imprint of the parent universe in our initial conditions, in the specific values of the fields at the moment of the bounce, in the detailed structure of the quantum state that emerged from the transition. But we cannot send a message back. We cannot say hello. We cannot ask questions about what came before, because before is on the other side of a horizon that seals us in. And yet the connection is not meaningless. The fact that we came from somewhere, that the Big Bang was not a true beginning but a transformation, that the universe has a history that extends beyond its own apparent origin, this changes the meaning of existence. We are not alone in the sense of being the only cosmos. We are part of a lineage, we have ancestors, we may have siblings. The black holes in our own universe, if the picture is correct, are doing the same thing right now, each one spawning a new universe inside itself, each one giving rise to a new Big Bang, a new expansion, a new history. We are part of a branching tree that extends in both directions, backward to the parent and forward to the children, and every branch is a universe, and every universe is someone else's interior. This is the picture that loop quantum gravity and torsion cosmology together suggest. It is not proven, it may never be proven. The observational tests we have discussed are difficult, and even a successful detection of a white hole burst or a CMB anomaly would not constitute proof of the full multiverse structure. But the picture is consistent with everything we know. It is mathematically coherent, it is physically plausible, and it is, in a strange way, beautiful. Let your thoughts drift with that for a moment. Let the scale of it wash over you without trying to grasp it too tightly. There is a question that arises naturally here, a question that has been hovering at the edge of this entire journey. If our universe is the interior of a black hole, and if that black hole sits inside a parent universe, then what about the parent? Where did it come from? Is it too the interior of a black hole in a grandparent universe? And what about the grandparent? Is there an infinite regress, a chain of cosmoses extending backward forever, each one nested inside the previous, each one the child of a collapse that happened in a higher level universe? The mathematics does not forbid this. There is no obvious reason why the chain must stop. The same physics that creates a universe inside a black hole could operate at every level of the hierarchy, producing an infinite tower of nested cosmoses, each one unaware of the ones above and below it, each one convinced that its Big Bang was the beginning of everything, each one discovering eventually that it was just another interior, just another bounce, just another branch of an infinite tree. This is vertiginous. This is the kind of thought that makes the mind reach for edges and find none. But notice that the vertigo is of a particular kind. It is not frightening. It is not threatening. It is the vertigo of vastness, not the vertigo of danger. You're not being warned about something. You're being shown something. Shown the possible depth of the structure that contains you. Shown the possible extent of the connections that link you to other times and places and cosmoses. The vertigo is wonder-shaped. It is the feeling of looking up at a clear night sky and realizing that every point of light is a sun, and that around some of those suns there are planets, and that on some of those planets there may be minds looking back. The same feeling but deeper, the same wonder but extended to the structure of space-time itself. And here is the strange thing, the quietly beautiful thing that emerges from this picture. The infinite regress is not a problem. In standard cosmology, the question, what came before the Big Bang, is treated as either meaningless or unanswerable. The singularity is a wall, but in the nested cosmology picture, the question has an answer, and the answer leads to another question, and that question has an answer too, and so on forever. This is not a failure of the theory, it is a feature. It means that existence is not contingent on a first cause, not dependent on something coming from nothing, not balanced on the impossible knife edge of an ultimate beginning. The chain extends backward and forward and in every direction, and there is no need for a start because there is no edge, no boundary, no point where the geometry breaks and the questions run out. The universe is not a thing that was created. It is a process that continues. It is a pattern that propagates. It is a structure that nests and branches and extends without needing an origin, because origin is not a concept that applies to it. This is not an evasion. It is not a way of avoiding the hard question. It is a different way of understanding what kind of thing a cosmos is. In the old picture, the universe is an object, a thing that exists, that has a beginning, that needs an explanation for why it is there rather than not there. In the new picture, the universe is a process, a transition, a bounce, a transformation of one geometry into another. And processes do not need beginnings in the same way that objects do. A wave does not need a first wave. A vibration does not need a first vibration. A pattern that propagates does not need a first pattern. It simply continues, extending in both directions, carrying information from one state to the next, transforming without ever truly starting or stopping. Let that thought rest quietly. Do not try to resolve it. Do not try to decide if it is true. Just let it be there, alongside the other thoughts, alongside the numbers and the images and the strange possibilities we have explored tonight. The night is deep now. The hours have passed. The mathematics has been dense at times, abstract at times, but always pointing toward the same quiet conclusion. The universe may not end the way we thought, may not have begun the way we thought, may be stranger and more connected than any previous generation could have imagined. The black holes that dot our cosmos are not tombs, they are wombs. The singularities that seem to mark the edges of physics are not walls, they are doors. And the Big Bang itself, that ultimate beginning, that first moment, that origin of origins, may have been just another bounce, just another transition, just another interior viewed from the inside. We have asked what a white hole is, and we have learned that it is the time reverse of a black hole, the outward explosion that mirrors the inward collapse. We have asked why quantum gravity forbids singularities, and we have learned that it is because the fabric of space-time itself has a graininess, a minimum scale, a resistance to being compressed beyond a certain point. We have asked what happens to the information that falls into a black hole, and we have learned that it may not be lost, that it may be transformed, encoded and eventually released when the black hole completes its long transition into a white hole. We have asked how long this transition takes, and we have learned that the answer depends on who is asking, A Planck instant for the matter inside, billions of years for an observer outside, the two descriptions connected by the strange geometry of the horizon. We have asked what this means for our own universe, and we have learned that the Big Bang may have been a bounce, that our cosmos may be the interior of a black hole in a parent universe, that we may be part of an infinite tree of nested cosmoses extending in both directions forever. These are not certainties, they are possibilities. The observational tests exist, the primordial black hole bursts, the CMB anomalies, the subtle signatures that a careful experiment might one day detect. But the tests are difficult and the detections may be decades or centuries away. For now, what we have is a picture, a story, a way of imagining the structure of reality that is consistent with the deepest physics we know. And that picture is haunting and beautiful and strange. You are lying inside a universe that is lying inside a black hole, that is lying inside a universe that is lying inside a black hole, and so on perhaps forever. The darkness around you is not empty. It is full of structure, full of nesting, full of the geometries that hold the geometries that hold you. The stars you see in the night sky are not the whole story. Behind them, beyond them, wrapped around the entire cosmos like a boundary you can never reach, is the horizon of the black hole that contains us. And beyond that horizon is the parent universe, vast and unknowable, going about its own business, unaware that inside one of its collapsed stars, a whole new cosmos is expanding, cooling, forming galaxies, evolving minds, asking questions about its own origin. And the black holes in our sky, the stellar remnants, the supermassive giants at the centres of galaxies, the primordial specks that may linger from the early universe, each of them may be doing the same thing. Each of them may be a parent, a doorway, a seed. Inside their horizons, beyond the reach of any signal we can send or receive, new universes may be forming right now. New Big Bangs may be happening. New histories may be unfolding. We cannot see them. We cannot contact them. But they may be there, nested inside the structures we observe, hidden behind the horizons we study, waiting to be discovered not by observation, but by the quiet work of theory, by the patient accumulation of mathematical consistency, by the slow recognition that the universe is deeper than it looks. This is where the journey ends, but it is not a conclusion. It is an opening. The questions do not close, they multiply. What is the physics of the parent universe? Is it the same as ours or different? What determines the initial conditions of a bounced cosmos? Is there selection, evolution, a kind of cosmic natural selection that favours certain physical constants over others? How many levels does the nesting extend? Is there an ultimate structure, a ground floor, a final cosmos that contains all the others? Or does the regress truly go on forever, infinite in both directions, bottomless and topless, a hierarchy without a foundation? We do not know. The mathematics does not tell us. The experiments cannot reach that far. But the fact that these questions can be asked, the fact that they make sense within the framework we have built, the fact that they are physical questions rather than metaphysical ones, this is itself a kind of progress. The boundary between the knowable and the unknowable has shifted. The edge of physics has moved. And what was once pure speculation, the idea of a multiverse, the idea of a cosmos with a history beyond its own Big Bang, the idea of a universe that is part of a larger family, has become, slowly, tentatively, a subject of serious scientific investigation. The night is patient. The mathematics will hold. And the picture we have built tonight, this strange, beautiful, vertiginous picture of a cosmos nested inside a cosmos inside a cosmos, each one born from a collapse and a bounce, each one carrying the imprint of its parent and the seeds of its children. It is not going anywhere. It will still be there when the darkness lifts. It will still be there when the experiments are done, when the observations are made, when the next generation of physicists takes up the question and pushes the boundary a little further. For now, let your breathing slow. Let your thoughts settle like sediment in still water. The universe around you is vast and strange and connected in ways you have only begun to glimpse. The Big Bang that started it all may have been the inside of someone else's ending. The black holes that punctuate it may be the beginnings of someone else's everything. You are part of a lineage that extends beyond the horizon, beyond the boundary, beyond the edge of what you can see or touch or measure. You are nested. You are held. You are the interior of a process that began elsewhere and will continue elsewhere, transforming without ending, bouncing without breaking, carrying the pattern forward into structures you cannot yet imagine. And if you fall asleep now, that is all right. The universe does not need you to stay awake for it. The mathematics does not need your attention. The tree of cosmoses will keep branching, the bounces will keep happening, the white holes will keep waiting at the end of their long, slow transitions, whether you're awake to wonder at them or not. Sleep is just another transformation. Consciousness fades and returns, the pattern continues, the process goes on. The Big Bang may have been the inside of someone else's collapse, and somewhere, in some other branch of the tree, another mind may be lying in another darkness, wondering the same thing, reaching the same conclusion, feeling the same quiet awe at the depth of the structure that holds them both. The darkness is full, the silence is thick with geometry, and the universe, this vast and ancient and expanding cosmos, is resting inside something larger, just as you are resting inside it, just as the night is resting around you now, patient and deep and unafraid of the morning.